Right, so 6.2 is the stereo center. So that kind of leads me, that last thing I just said leads into here, which is the chiral center. In order to have a chiral center, you have to have a carbon must have 4 different groups around the sp3 center. Okay, so just like we saw a carbon with a hydrogen, with a bromine, with a chlorine, with an OH, all right, this would be a stereo center, a chiral center, a stereogenic center. These are all the same terms. It seems like every 5 years they change the name. I'm going to call them all of them because you might hear all of them. So really any carbon with 4 different groups on it is stereogenic. That means you can have the left-handed version or the right-handed version of it. Okay, now this is different from constitutional isomers. People still have trouble distinguishing between the two. Constitutional is where the atoms are connected to a different molecule, a different atom on your molecule. So the molecule is a different molecule. It's not the same molecule. Notice these are the same. You have the same atoms. They are connected in the same place. It's just in 3 dimensions, they are not the same. They cannot be superimposed. Okay? So let's go back to the stereo centers. So you can quickly determine if you have a stereo center on a molecule by looking at if they have 4 different groups around it. Okay? So what I'm going to do is put this on pause, see if you can find the stereo center in this molecule, and we'll come back. Okay, the stereo center is this carbon right here. That carbon right there is a stereo center. How do I know? There's 4 different groups attached to it. Okay? Now, let's go over this. First of all, it has to be sp3. Okay? Second of all, 4 different groups. Now, the groups, I didn't say it. I wanted to see if you can figure this out. But the groups is just like what we learned when we determined E and Z. All right? You look for, if you have a tie, you go to the next atoms. And then if the next atoms are different, then it's different. If you keep going around and they're all the same groups and eventually meet, or they have the same exact groups, you do not have a chiral center. So notice I have a CH3, that's one different group. I have a hydrogen here. I didn't draw it in, but you have to remember there's a hydrogen. Now if you look here, I have a tie, CH2, CH2. So then I go to the next atom. I have a carbon with a carbonyl and a carbon with a double bond carbon. These are different. So technically this carbon has 4 different groups around it. So that is the chiral carbon. This is not chiral because it's not sp3. Okay? Either is this one. Plus you don't have 4 different groups around it. Okay? So that carbon is the chiral carbon. Let's do another one. All right, the chiral carbon in this case is that carbon right there. That carbon is chiral. I have a methyl group. I've got a hydrogen. I got a CH2, CH2. Those are equivalent. But then I have a CH2, CH3. Those groups are different. Or you can just look at the whole group if you wanted to. This is 2 carbons. This is 3 carbons. These are different groups. Okay? So that's how you can determine if a carbon is going to be chiral. Look to see if it has 4 different groups. All right, next concept is this concept called optical activity. This is a physical phenomenon, or a physical property. Let's call it physical property of molecules that are chiral. All right, what they do is they have an effect on how light travels across the molecule. All right, and it uses what's called plane polarized light. This is an experiment that is used to determine if a molecule is chiral. So let me kind of give you the quick version of what the experiment is, and like I said, you can read more about it in your book, or if you want to look online for a video. Okay, but imagine I have a light bulb. Okay, and the light bulb is shining light waves in multi-directions. So you have an infinite, so all these are light waves. All right, what you have is you have a polarizer in front of it. All right, polarizer, if anyone has polarized sunglasses, you know that light only travels a specific wavelength of, or the certain light is able to travel through the polarizer. So you have all these wavelengths of light, but if it's polarized going up and down, only those light waves are allowed to travel through. Everything else is blocked out. All right, hence the name plane polarized. It's polarized. Only light going in the direction of the slits in your polarizer are allowed to travel through. So all this other light is blocked out. Only the light going up and down is allowed to go through. All right. Then you have your sample. Okay, so here's your sample. All right, and imagine this molecule is chiral. All right. The chiral compounds have an effect on how light travels through it. So when this plane polarized light starts traveling through the sample, the chirality of the molecule actually changes the direction of the light. So the light's traveling through, the molecule has an effect on the light, and now the light is traveling this way. Okay, it's a very interesting phenomenon or property that molecules have. And what you do is you have an analyzer, it's a dial, all right, where this is 0, this is 90, this is negative 90, this is plus 90. So however the light is traveling, the light is recorded at that number. Let's say this is a positive 45, all right. So this particular sample, okay, whatever the molecule is, you know, one of the properties is that if you have 100% of this sample, let's call it sample A. If you have 100% of sample A, you can tell that it's chiral because it will shift light positive 45. All right. Now you can either put a positive or you can put a D. You might see D sometimes, or the word for D is the dextrorotatory. Okay. So the D implies that the light shifts to the right. Now, if you had the enantiomer of that compound, right? So if you had 100% of enantiomer B, how do you think it's going to shift the light? So let's say I have the exact mirror image of it. What do you guys think? Okay. Well, the light's going to shift it negative 45. So the enantiomer shifts it exactly opposite direction, and rotatory. So L is sometimes used. So in the name, they'll have it D and then the name of the compound. All right, like a D-lysine. All right, lysine is an amino acid, or they'll have L-lysine. Or they might have it as positive lysine. Or they might have it as negative lysine. Right? These are all different ways of how to name the molecule. And this is a physical phenomenon, how you can tell if your molecule is chiral or not. Now, one interesting note is that if you have a 50-50 mixture of enantiomers, 50-50 mixture of enantiomers, how do you think it's going to shift the light? Well, half of it shifts it to the left, the other half of it shifts it to the right, so they average out, so you actually get 0 on the analyzer. All right, so even though your molecules are chiral, it's going to show up as 0. This is what's called a racemic mixture. All right, a racemic mixture is basically when you have 50-50 of both enantiomers. All right, if you have 100% of one, it's called enantiomerically pure. Enantiomerically pure. So if you have 100% of the R, you have an enantiomerically pure, the D, you have 100% enantiomerically pure D, or you have 100% enantiomerically pure L, or you have a racemic mixture. Now, you could have a variation like 75% of one and 25% of the other, but we're not really going to get into that.